You have one model and a wall of knobs: learning rate, batch size, optimization method, depth, and dropout. Every change means training again. There is no formula that points straight to the best setup. If you cannot try everything, where should the next trial go? By the end, you will be able to read an Optuna study and understand what the objective, trial, sampler, and pruner actually do. More importantly, you will know why TPE selects a new configuration instead of merely copying a few lines of Python. First, separate parameters from hyperparameters. Parameters, such as weights, are learned by the model during training. Hyperparameters, such as the learning rate or architecture, are chosen outside that process. Optuna mainly searches for the second group. Put those hyperparameters into a vector called x. Train the model with x, measure validation loss or another metric. And you get why that entire training and evaluation pipeline is the objective function. X goes in, y comes out. That function is usually a black box. We do not know its true equation, we have no direct gradient with respect to the hyperparameters, and every call may be expensive. Even the same configuration can change slightly because of seeds, mini-batches, or data noise. Grid search divides every axis into fixed points and tests every combination. Random search samples the space. Neither method meaningfully uses previous outcomes to choose the next point. Bayesian optimization does. Trial history becomes data for the next decision. Bayes is not magic that discovers the answer. It is a rule for updating beliefs when new evidence arrives. Before seeing data, we have a prior. How well the data agrees with a hypothesis is the likelihood. Combining them gives us the posterior. The formula says, the probability of a hypothesis after observing data equals likelihood times prior, divided by evidence. The denominator normalizes the probabilities so they sum to 1. The key idea is in the numerator. New evidence updates an old belief. In Bayesian optimization, a hypothesis does not have to be one answer. We can place a prior over the entire unknown objective function. Before any trial, we are effectively holding many possible surfaces that could explain the relationship between hyperparameters and score. When a trial finishes, we observe one pair, x and y curves that disagree with the new point lose weight. Curves that agree survive. The remaining distribution is the posterior, our updated belief about the objective. So Bayes does not directly tell us which point to try. It only tells us what the objective may look like after the data we have, and where we remain uncertain. Choosing the next trial requires another decision layer. The real objective is too expensive to call everywhere, so we build a cheaper surrogate model. It does not replace real training. It only ranks which points are worth sending to the real objective next. In classical Bayesian optimization, the surrogate is often a Gaussian process, or GPA Gaussian process is a distribution over functions. Its kernel describes how strongly 2 points in hyperparameter space should influence one another. After conditioning on completed trials, the Gaussian process gives 2 outputs at every x, a predicted mean and uncertainty. Near measured points, the uncertainty band is usually narrow. In unexplored regions, it is usually wider. But always choosing the best mean only exploits the current winner. Always choosing maximum uncertainty only explores. Bayesian optimization must balance exploitation, digging deeper where results are good, with exploration, checking places where we are still blind. That job belongs to the acquisition function. It is a cheap function that reads the surrogate posterior and scores the usefulness of each candidate. The point with the highest acquisition value is sent to the real objective next. One common acquisition is expected improvement. For minimization, improvement is how far the loss may fall below the best result seen so far. Because the result is still a distribution, we take the expectation of that improvement. A point with a decent mean and large uncertainty can still have high expected improvement because it might surprise us. A well-known point that only matches the current best can score lower. Exploration and exploitation emerge from the same calculation. The complete loop is: fit the surrogate on old data, optimize the acquisition to get the next x, run the real objective, observe a new y, and update the posterior. Bayesian optimization is this sequential process, not the Gaussian process alone. If the objective is noisy, one unusually strong trial may not represent a truly strong configuration. The surrogate must model noise, or the evaluation must be repeated. Bayesian optimization does not remove uncertainty. It makes uncertainty part of the decision. In Optuna, a study is the complete optimization task. It holds the direction, sampler, pruner, storage, and trial history. With one metric, the direction is minimize or maximize. Multiple metrics create a different multi-objective problem. The objective is the function you write. It receives a trial object, requests hyperparameter values, trains a model or runs an experiment, and returns an objective value. Optuna does not understand your model. It coordinates the proposed values and the result you return. A trial is exactly one call to the objective. It is not one epoch, and it is not the model itself. A trial stores parameters, distributions, the objective value, intermediate values, timing, and the state of that run. A trial may be waiting, running, complete, pruned, or failed. A complete trial has a final result. A pruned trial was intentionally stopped. A failed trial hit an uncaught error. Those states must not be treated as equivalent when analyzing a study. Parameters are created through suggest methods. Float means a real number, integer means an integer, and categorical means a discrete choice. The range, log scale, and conditional relationships are defined by the objective author. Optuna does not know a sensible learning rate range by itself. The sampler answers this question: which parameter values should the next trial use? It reads the search space and study history before the objective runs. Random sampler, TPESampler, and GPSampler are different strategies for that same role. The pruner acts at a different time. While the objective runs, the code reports intermediate values. Then should prune asks whether the trial should stop early. The sampler chooses a configuration. The pruner decides whether that configuration deserves more resources. Study, trial, sampler, and pruner are not four names for one algorithm. The study is the ledger. A trial is one experiment. The sampler chooses a new experiment. The pruner may end an experiment that is already running. This is where many explanations go wrong. Optuna does have a GP sampler in the classical Gaussian process style. Fit a GP to the objective, then optimize an acquisition function. But for single objective studies, the current stable default sampler is TPESampler, not GPSampler. TPE means tree-structured Parzen estimator. It still belongs to sequential Bayesian optimization, but instead of directly modeling P of y given like a Gaussian process, it mainly models P of x given y. In stable version 4.9 at the time of production, TPE uses random sampling until 10 startup trials finish. The reason is simple. Without data, it cannot estimate meaningful good and bad densities. After startup, TPE ranks trials by objective value. For minimization, it chooses a threshold y star and splits the observations into a low-loss good group and the rest. For maximization, the meaning of good and bad is reversed. The gamma function controls how many trials enter the good group. In the stable 4.9 source, the default is the ceiling of 10% of completed trials, capped at 25. A smaller gamma focuses more. A larger gamma gives the good density broader support. From the good group, TPE estimates L of x, which parameter values often appear in good trials. From the remaining trials, it estimates G of x, which values often appear outside the good group. For a continuous variable, imagine placing a bell-shaped kernel around every observation. Adding the kernels creates a mixture density. Categorical choices use discrete probability masses. This is the Parzen estimator part of TP. Now Bayes returns. We want to know how good y may be after choosing x, or P of y given. But TPE has modeled P of x given y. Bayes' rule lets us reverse the direction between those conditional probabilities. Substitute those two densities into expected improvement. The quantity to optimize is proportional to the inverse of gamma plus 1 minus gamma, times G of x divided by L of x. Expected improvement is therefore large when L is large and G is small. In plain English, find parameter values that resemble good trials but are uncommon in the rest. A large L alone is not enough, because one region may be common in both good and bad trials. The ratio L over G creates the distinction. TPE does not scan the whole space for the largest ratio. In stable 4.9, it uses 24 expected improvement candidates by default. It samples candidates from the good density, scores them by L over G, and selects the best one. The real objective runs with that candidate and creates a new trial. The trial enters history, the good threshold changes, both densities are refit, and another candidate is generated. TPE also follows the loop: model, choose, measure, update. Tree structured refers to a search space with branches. If the optimization method is atom, one set of parameters may become active. If it is SGD, momentum may appear instead. Parameters inactive in the current branch should not be treated as if they always exist. Optuna lets you define those branches with normal Python control flow inside the objective. This is a define-by-run search space. It fits TPE because real hyperparameter configurations are often not one fixed rectangular box. Another nuance is independent versus multivariate. TPE independent mode estimates each parameter separately, so it can miss relationships, such as a high learning rate working only when batch size also changes. Multivariate TPE tries to model them jointly. In stable 4.9, multivariate mode in the TPESampler is off by default. Turning it on is not automatically better. With little data and many dimensions, joint density estimation becomes harder. This choice must be benchmarked on the real objective. So TPE does not merely shrink a box around the best trial forever. It builds densities, samples candidates, and preserves a chance to test other regions. Simply cloning the best trial would destroy exploration and make the search easy to trap. Pruning solves a different question. Should this running trial be completed? At each checkpoint, the objective can report a validation metric. The pruner compares the current learning curve with its rule and decides whether to stop or continue. Median pruner, for example, compares the current intermediate value with the median of previous trials at the same step. An unpromising trial can be pruned, but a slow-starting model may later become strong, so pruning always trades resources for the risk of stopping the wrong trial. TPE can work with a pruner, but they do not share one job. TPE chooses parameters before a trial begins. The pruner reads intermediate values after it has started. A study can replace the sampler while keeping the pruner, or the other way around. Bayesian optimization is naturally sequential. The latest result guides the next point. With parallel workers, results from running trials do not exist yet. Workers can accidentally choose nearby regions and reduce the information gained from the batch. TPE offers a constant liar option that penalizes regions near running trials, reducing the chance of similar suggestions. It can help when objectives are expensive and long-running, but it remains a heuristic for unobserved information, not a real result. A bad search space defeats a good sampler. Learning rate should often use a log scale when several orders of magnitude are plausible. Irrelevant parameters only add dimensions. Conditional branches should reflect which parameters are actually used. A bad objective is even more dangerous. Optimizing the test set leaks test information into model selection. If the metric does not represent the product goal, Optuna will become excellent at optimizing a number that has no value. Bayesian optimization does not guarantee the global optimum under a finite budget. It is especially useful when the objective is expensive, and each evaluation must be chosen carefully. If evaluation is extremely cheap or massively parallel, random search can remain a very strong baseline. The best trial is only the best result observed in that study. Before deployment, retrain it, test on held-out data, and check stability across seeds. Optimization selects candidates. It does not replace a validation process. The final practical bonus is Numba JIT, but Numba does not make TPE choose a smarter candidate or make the sampler itself faster. Total time contains both sampling and the objective. Numba can only shorten the objective when Python numerical code is the bottleneck. Do not put NJIT around the entire objective that receives a trial. Trial is a complex Python object and does not fit no Python mode. Keep Optuna orchestration in Python, then pass scalars and NumPy arrays into a separate compiled numerical function. The objective calls trial suggest methods as usual, then passes the hyperparameters into an evaluate core function. The core contains only numbers, arrays, and loops supported by num. It returns a number to the objective, which returns that value to the study. Numba compiles lazily. The first call with a new data signature includes compilation time and may even be slower than Python. Warm the function once before study optimize, keep data type stable, and use cache equals true where it makes sense. Numba is a strong fit for back tests, simulations, custom metrics, signal processing, and numerical loops written in Python. These objectives repeat the same calculation many times with different hyperparameters. But if the objective mainly trains PyTorch on a GPU, calls native libraries such as XGBoost, reads files, or waits for a network, Numba does not accelerate the expensive part. Adding NJIT to a Python wrapper cannot turn a GPU or an external library into Numba code. Parallel equals true can use multiple CPU threads inside one trial. But if Optuna also runs several trials at once, those two parallel layers can fight for every core. Allocate thread budgets explicitly instead of enabling every level of parallelism at the same time. Fast math may run faster by relaxing floating point rules. That can also change results by reordering arithmetic or changing the treatment of special values. Do not enable fast math merely because its name sounds fast. A valid benchmark separates cold start, warm execution, and total study time. Both versions must agree within an acceptable tolerance and use the same data types, data, and seed. Only then can you claim that Numba made the search faster. If the objective dominates runtime and Numba accelerates it, the whole Optuna study can finish much faster. If the cost lives in the GPU, input-output, or the sampler, the gain may be almost zero. Profile first, JIT second. Now the complete Optuna loop reads like this. The study stores history. The sampler reads it and proposes parameters. The objective evaluates them inside one trial. The pruner may stop that trial early. The value returns to the study, the sampler updates its model, and the next loop begins. The essence of Bayesian optimization is not guessing correctly on the first try. It uses probability to decide which next evaluation is worth buying. A Gaussian process does this with a posterior over the objective. TPE does it with two densities, good trials and the rest. Which topic should go deeper next? Gaussian processes or pruning? Reply with GP or pruning.